This is lecture number 28 of our course on fundamentals of transport processes. Welcome. As we were discussing in the last lecture, two-dimensional potential flows. So, just to recap, potential flows in the limit of high Reynolds number, inviscid, viscosity is set equal to 0, and irrotational. What is meant by irrotational is that the vorticity, which is equal to del cross u, this is equal to 0. And if the curl of a vector is equal to 0, it can always be expressed as the gradient of a potential. That is the reason for the name potential flow. Okay. So, therefore, I can always write the velocity as the gradient of a potential. And this expression can be substituted into the mass and momentum Navier-Stokes equations. The mass conservation equation requires that the divergence of the velocity is equal to 0. And what that straight away implies is that the Laplacian of the potential has to be equal to 0, that is del square phi is equal to 0, where phi is the velocity potential. The momentum conservation equation, in the absence of viscosity, minus grad p plus mu, the viscosity is equal to 0. So, there can at most be a pressure force, a pressure plus a body force. We have neglected the viscous term in the conservation equation, and we have seen that this can be reduced to an equation of the form gradient of p plus half rho u square plus rho d phi by dt. Okay. This is equal to 0. Okay. In this particular case, I am assuming that this pressure can be written as minus of the gradient of a potential. In other words, it is a conservative force. Okay. The body force is a conservative force. So, it can be written as minus grad phi, gradient of the potential, and that potential term can be incorporated into the definition of the pressure itself. So, even though the momentum conservation equation is a vector equation for 3 components, this can be reduced to a statement that just says that the gradient of a scalar function is equal to 0. That means that that scalar function has to be a constant. Okay. Is equal to some constant. Okay. So, these are the mass and momentum conservation equations. The mass conservation equation is a Laplacian equation solved for the velocity potential, and the momentum conservation equation can be solved to obtain the pressure. The stress tensor in this case just contains only the pressure alone, okay, minus p times delta ij. So, it is isotropic, it contains only the pressure. A consequence, 2 consequences that we discussed in the previous lectures. Since we have neglected the viscous terms, it is not possible to satisfy both the tangential and normal velocity or stress conditions. For a potential flow, one can satisfy only the normal velocity or the normal stress continuity conditions. One cannot satisfy the tangential velocity or tangential stress continuity conditions. So, we had seen how to solve this potential flow problem for a sphere in 3 dimensions, and we managed to get the result that for this sphere to go at constant velocity, there need be no force applied on the sphere. In other words, that there is no drag force due to the sphere moving at a constant velocity. In the last class, we also showed that there is no drag force for an object of any shape moving at constant velocity. The reason is because we have neglected viscous dissipation in the potential flow equations, and therefore, there is no change in energy. The energy is not dissipated by viscosity, energy is conserved. If energy is conserved at constant velocity, there is no need to put in energy in order to keep the object in a state of motion, and therefore, you need no net force in order to move the object at a constant velocity. When the object is accelerating, of course, you do need a net force, and that force is equal to the added mass times the acceleration. For a sphere, we saw that the added mass is equal to half the mass of the fluid displaced by the sphere. For objects of other shape, one can still calculate an added mass either from the kinetic energy or from the force, okay, either from the total kinetic energy of the flow field. So, in that case, the kinetic energy will be equal to half added mass times u square, or from the force required, okay. And in general, that will be some other fraction of the mass displaced by the sphere. So, in the last lecture, we had restricted our discussion to two-dimensional potential flows. Okay. It is an important class of flows where you have variations only in two directions, the x and y direction. You could have, for example, some object, okay, around which there is fluid that is flowing in two dimensions. Okay, and we are looking at the potential flow equations for flows of this type. All objects are, of course, three-dimensional. What is meant by a two-dimensional object is that there is no variation in the third dimension. In other words, in the direction perpendicular to the plane of the board, there is no variation in either the shape of the object or the velocity field. So, if we take a cross section through this object, there is no variation in the third direction perpendicular to this cross section. Therefore, we can analyze the flow in this two-dimensional plane alone. Okay. All long and slender objects can be approximated by two-dimensional objects. An airplane wing, for example, the variation of that wing along the third direction is actually small compared to the shape in the two dimensions perpendicular to the wing. So, I can analyze the flow in a cross section, okay, perpendicular to the direction of the axis of the wing. So, it is understood that there are three dimensions, but we are analyzing only the two-dimensional flow in the plane perpendicular to the axis of the object. That axis is now perpendicular to the plane of the board, and therefore, there is no variation in that direction. So, all quantities that we will calculate, such as the force on the object or the energy of the flow, are all per unit length in the direction perpendicular to the flow. Okay. So, they will have what dimensions of length inverse times what you would normally expect. So, in this case, for the force on this object, it will be a force per unit length in the plane perpendicular to the flow. Okay. So, for example, if you had a long cylinder, you cannot calculate and if you approximate that cylinder as being of infinite length, you cannot calculate the total force on that entire cylinder. You can only calculate the force per unit length. That multiplied by the length will give you the total force. Okay. If the length is long enough, you would expect that somewhere away from the ends, the flow is going to be two-dimensional. Of course, there will be a variation at the ends, but provided that is small, it makes only a small contribution to the net force on that cylinder. It is good approximation to consider the cylinder to be two-dimensional, calculate the force per unit length and then multiply it by the length in the third direction. So, that is the kind of philosophy that we use for analyzing two-dimensional flows. So, we are looking for flows that satisfy the potential flow equations in this two-dimensional plane. Okay. And if you recall, we had started the discussion in the previous lecture. Okay. Rather than work separately in the x and y coordinate, we can consider some point in this plane as simply representing a number in the complex plane, a complex number in the complex plane. Okay. So, any location will have one position in the complex plane which has a real part plus an imaginary part. Okay. So, we will work in terms of the complex number z itself rather than individually in terms of x and y. The reason we can do that is as follows. Okay. If you have any function, any function of z, this can be any function z square, z cubed, cos z, exponent of z, and so on. This function is considered analytic if I can write f at z plus delta z minus f at z in the limit as delta z goes to 0 can be written as df by dz times delta z. In other words, I can define a derivative of this function in the complex plane, a complete derivative or a total derivative with respect to the complex variable z rather than partial derivatives with respect to x and y. This complex function f is in general a complex function, because z square, for example, will have a real part and an imaginary part. So, if this function f of z will in general have a real part plus an imaginary part. And these two, real part and imaginary part, have to be related, or the partial derivatives with respect to x and y have to be related if the function f is analytic. In other words, if I require that if I go from a location z to another location z plus delta z, and if I can write delta f, which is f of z plus delta z minus f of z, as this times df by dz, a derivative times delta z, then there is a relationship between the real and imaginary parts of this complex function z. The relationship is partial phi by partial x is equal to partial psi by partial y. Partial phi by partial y is equal to minus by partial x. Cauchy-Riemann conditions they are called. These conditions have to be satisfied for the partial derivatives of phi and psi if the function f is an analytic function. And just by simple algebraic manipulation, you can show that if these conditions are valid, then del square phi has to be equal to 0 and del square psi has to be equal to 0. So, for the complex function f of z, the requirement of analyticity requires that both the real and imaginary parts of this function satisfy the Laplace equation. For solving for potential flow, we require that the potential field satisfies Laplace equation. Every real part of every analytic function satisfies Laplace equation. That means that the real part of every analytic function represents some potential flow, provided it satisfies the boundary conditions that are prescribed on the surfaces in 2 dimensions. Note that in 2 dimensions the surface reduces to just a line in the plane, because you are assuming that it is infinite in the third direction. So, we can identify the complex function f as a complex potential. We can identify the complex function f as a complex potential. Then the real part of f is what is identified as the velocity potential phi. So, it is no coincidence that I wrote f in terms of this function phi here. So, the real part of every complex function represents the velocity potential of some flow. So, we have f is equal to the complex potential, which is phi plus I psi. We can identify phi is equal to the velocity potential, which means that ux is equal to partial phi by partial x and uy is equal to partial phi by partial y. Okay. And from the Cauchy-Riemann conditions, we know that partial phi by partial x is also equal to partial psi by partial y, and partial phi by partial y is minus partial psi by partial x. What that means is that the imaginary part of the function f is just the stream function. The imaginary part of the function f is just the stream function. Okay. I can define the complex velocity w is equal to df by dz. Okay. And we saw that in the last class, when this is expressed in terms of the two components of the velocities ux and uy, this can be written as ux minus I uy. And one can also express this in terms of the velocities in a r theta coordinate system, in a polar coordinate system. Okay, so if I am at some location z, okay, this is x, this is y, this is theta, okay, and we know that the complex number z is equal to r e power I theta, which is equal to x plus I y, where x is r cos theta and y is r sin theta. Okay. So, the radial direction, the unit vector in the radial direction is in this direction, and the theta vector is along the direction of increasing theta, which is the anti-clockwise direction in this plane. Okay. And these are x and y. Okay. So, I can also express w in terms of u r and u theta, the components of the velocity along the radial and the theta direction. Okay. And expressed in terms of this, it turns out to be equal to u r minus I u theta into e power minus I theta. So, that is how the complex potential and the complex velocity are related to the potential and the velocity in the two-dimensional coordinate system, x y coordinate system. So, now we showed that every potential function or every analytic function in the complex plane, the real part of that function represents the potential for some velocity field. The imaginary part represents the stream function for that same velocity field. So, one can ask the question, what do common forms of this function, what velocity fields do they represent? Okay. So, we look at some common, some simple functional forms and ask the question, what is the kind of velocity field that is represented by this particular form? So, the simplest form to take, okay, of course, the simplest form is a constant, but if you take the derivative of that, it ends up being 0. So, the velocity is 0. So, this just represents a fluid at rest. But the next simplest form that one can take is a function of the form u times z. Okay. So, that means that the complex velocity for this case w is equal to just u. Okay. And we know that the velocity field for this has to be, can be written as ux minus I uy. Okay. So, what this means is that the velocity ux is equal to capital U and uy is equal to 0. So, ux is a constant, it is equal to capital U and uy is equal to 0. That means that you have a constant velocity u everywhere. The velocity is just a constant everywhere, independent of position. Okay, so, potential that is linear in z, of course, gives you a constant velocity, that is no surprise. Okay. You could have taken, in this particular case, I took u as a real number. I need not have done that. Okay. The next simplest thing I could consider is to take u e power I alpha z, okay, which means that w is equal to u e power I alpha, which will be u into cos alpha minus I sin alpha is equal to, sorry, ux minus I uy. Okay. Now, what that means is that ux is equal to u cos alpha and uy is equal to minus u sin alpha. So, this is a flow which is at some angle, it is not along the x axis, but rather it is inclined at an angle to the x axis. Okay, so it is a flow that looks something like this. Okay, there is an angle alpha with respect to the x axis. Okay. And ui is negative, so it is actually going down at an angle of minus alpha with respect to the x axis. Okay. The next more complicated form, f is equal to let us call it as a z square, okay, which implies that w is equal to 2a z, okay, df by dz. Okay. So, this can be written as 2a r e power I theta. Okay. Now, this I could write it as u a r 2 a r into cos theta plus I sin theta, and then write x and y in terms of u x and u y in terms of w, using the relationship that this is equal to u x minus I u y. Okay. But for our physical understanding, it is more convenient to write this in a radial polar coordinate system as u r minus I u theta e power minus I theta. Okay. So, I will use the expression that w is equal to u r minus I u theta e power minus I theta, and then use this in order to find out what is the expression for u r and u theta. Okay. So, therefore, I find that u r minus I u theta is equal to 2 a r e power 2 I theta is equal to 2 a r into cos 2 theta plus I sin 2 theta. Okay. So, therefore, the velocity field satisfies u r is equal to 2 a r cos 2 theta, u theta is equal to minus sin 2 theta. So, now let us try to plot this velocity field. Okay. As you know, r is the radial coordinate and theta is the polar coordinate, okay, the angle from the x axis. Along the x axis, theta is equal to 0. Okay. Along the x axis, theta is equal to 0. That means that u r is equal to 2 a r, okay, because theta is equal to 0 along the x axis. Therefore, u r is equal to 2 a times r. Okay. So, it is a velocity that is increasing as you go outward. Okay. The velocity is proportional to 2 a r. So, it increases with radius as you go outward. Okay. Along the y axis, theta is equal to pi by 2. Okay. That means that cos 2 theta is cos of pi, which is minus 1, sin 2 theta is sin of pi, which is 0. Therefore, u r is equal to minus 2 a r and u theta is equal to 0. So, the radial velocity is coming inwards. Okay. It is in the negative r direction, it is equal to minus 2 a r because cos 2 theta is minus 1. Okay. So, therefore, the velocity is coming inward, okay, and once again the magnitude is decreasing as you come in. Okay. So, the magnitude of the velocity is still proportional to r, and however, it is coming inwards. Okay. It is coming towards the origin along the y axis, it is going away from the origin along the x axis. What about in between? Okay. If you take at an angle of pi by 4, for example, take it at an angle of pi by 4, for example, okay, you find that at theta is equal to pi by 4, 2 theta is pi by 2. So, cos of 2 theta is equal to 0. That means that there is no radial component of the velocity. Sin 2 theta is 1. That means that u theta is minus 2 a r. Okay. So, once again the radial direction is along the line, the dotted line that I have shown here at pi by 4, it is radially outward. Okay. So, the component of the velocity along this radial outward direction is equal to 0. Okay, that means that there is no component along the radial direction. The only component is along the theta direction, perpendicular to that one. Okay. Note the direction of increasing theta is anti-clockwise, okay, whereas u theta is negative in this case, because sine 2 theta is 1. So, u theta is minus 2 a r. So, therefore, the velocity is in the clockwise direction along this. Okay. So, the velocity is in this direction. Once again, u theta increases proportional to r as r increases. Okay. So, you are going to get a velocity that looks something like this. Okay. So, it is inward along the y axis, outward along the x axis, and it is perpendicular to the position vector along the pi by 4 line. And if you plot the velocity at various intermediate points, you will get a velocity field that looks something like this. You get a velocity field that looks something like this. Okay. So, this is only in the first quadrant. You could of course plot it for other quadrants, and I will leave it as an exercise. It is quite simple to do. You get a velocity that is radially outward along both the positive and negative x axis. It is inward along both the positive and negative y axis, okay, and you end up with a velocity that looks something like this. You end up with the velocity. So, I said that this represents some potential flow which satisfies the known normal velocity boundary conditions at the bounding surfaces. One can turn the argument around and say that the bounding surfaces are those surfaces along which the normal velocity is equal to 0. Okay. For this particular flow, valid boundary surfaces are those surfaces for which the normal velocity perpendicular to that surface is equal to 0. And clearly, you can see that there are 4 bounding surfaces here, both the x axis plus and minus. The velocity is radially outwards, it is along the axis. There is no velocity perpendicular to the axis. So, that constitutes a boundary surface for this flow. Similarly, for the y axis, the velocity is inward, it is along the axis, parallel to the axis. There is no normal velocity to the axis. So, that constitutes a valid boundary surface. So, therefore, this complex function a z square represents a flow in a corner whose axes are 90 degrees apart. Okay. It represents the flow in a corner in which the angle between the two surfaces at that corner is equal to pi by 2. Okay. So, that is for a z square. One can of course consider any higher power of z, okay, any polynomial approximation for z. So, if I consider a general function of the form f is equal to a times z power m, the complex velocity is equal to df by dz is equal to m a z power m minus 1. Okay. And I can write this as in the polar coordinate system as m a r power m minus 1 e power I into m minus 1 theta. Okay. This complex velocity is equal to u r minus I u theta e power minus I theta. Okay. So, therefore, I have m a r power m minus 1 e power I into m minus 1 theta is equal to u r minus I u theta e power minus I theta. Divide both sides by e power minus I theta to obtain is equal to u r minus I u theta. Okay. What this means is that the velocity is defined by u r is equal to m a r power m minus 1 cos m theta, okay, is equal to minus m a sine of m theta. Okay, so, those are the u r and u theta velocities. Okay. Now, we can plot these once again on an xy plane. Along theta is equal to 0, cos of m theta is equal to 1, because theta is equal to 0, sin of m theta is equal to 0. Therefore, u r is equal to m a times r power m minus 1, and u theta is equal to 0. So, that means that along the x axis you have a velocity that is only in the radial direction, radially outward. Okay. Okay, you have a radially outward velocity. The velocity magnitude increases as you go outward, proportional to r power m minus 1. Okay, so, the velocity magnitude is increasing as you go outward. Since the velocity is along the axis, along the line, the tangential to the axis, there is no normal velocity. So, this constitutes a valid boundary for the flow. Okay. Because whenever the velocity is radially outward, it is along the line from the origin. Therefore, that is a boundary. There is one other axis along which the velocity is radially outward. Okay. That is when cos of m theta is equal to minus 1, okay, and sin of m theta is equal to 0. So, along a boundary axis, the cos function has to be plus or minus 1 and sin function has to be equal to 0. Okay. Now, that is going to happen along an axis whose angle subtended is equal to pi by m. Okay. This angle is equal to pi by m, because if this angle is equal to pi by m, that means that cos of m theta is cos pi, which is minus 1, sin of m theta is sin pi, which is 0. Okay. So, for an angle of pi by m, the velocity is u r is equal to minus m a r power m minus 1, and u theta has to be equal to 0. Okay. Okay. So, along this axis, once again you have a velocity that is radial to the axis, but it is radially inward, because when the angle is pi by m, cos theta is equal to minus 1. Okay. So, I have a velocity that is radially inward. Once again, the magnitude of that velocity increases as you go further out. As r increases, the velocity magnitude increases as r power m minus 1. So, along the axis pi by m, you have radially inward, and along the axis 0, you have radially outward. You would expect that in between these two, okay, halfway in between these two, the velocity is actually in the theta direction. Okay. So, if I am halfway between these two, when the angle is pi by 2m, m theta is pi by 2. Okay, when the angle is pi by 2m, about halfway between these two, okay, pi by 2m, m theta is equal to pi by 2, and therefore, the velocity u r cos of pi by 2 is 0. So, there is no radial component. U theta cos of sin of pi by 2 is equal to 1. Okay. Theta is equal to pi by 2m, therefore, sin of m theta is 1, and u theta is minus m a r power m minus 1. So, you get a theta velocity that comes something like this. Okay. And this represents a flow in a corner once again, where the angle of that corner is now pi by m. Previously, for a z square, the angle was pi by 2. For a z power m, the angle is pi by m. Okay. So, when m is greater than 2, of course, pi by m is less than pi by 2. So, you get a flow in a corner in an acute angled corner. Okay. On the other hand, if okay, so this is for m greater than 2. Okay. If m is less than 2, of course, pi by m is between. Okay. So, this if I consider 1 less than m less than 2. Okay. If m is between 1 and 2, the angle pi by m is between pi by 2 and pi. So, this is the angle pi by m for m between 1 and 2, pi by m for m between 1 and 2. Okay. The angle is between pi by 2 and pi, and therefore, you get a flow in a corner that looks something like this, okay, in an obtuse angled corner. Okay. You get a flow in obtuse angled corner if the angle is between pi by 2 and pi, or m is between 1 and 2. Okay. This is for m greater than 2. For m is equal to 2, the angle w is equal to a z square. So, the angle is pi by 2. You get a flow in a right angled corner. Okay. For m exactly equal to 1, m exactly equal to 1, right, or f is equal to a times z to the first power. That is what we had solved first. When f is equal to a times z, w is equal to a. So, the velocity is a constant. So, that represents a flow in a corner. It is not a corner really, but it is just a straight flat surface. This subtended angle is just pi. Okay. The velocity field looks something like this. Okay. And m can of course be less than 1. Okay. M can be less than 1, okay, because the angle is pi by m. Theta can go anywhere from 0 to 2 pi. That means m can be less than 1, it can go down to a half. So, that pi by m is equal to 2 pi. Okay. So, if m is less than 1, what you get is an angle that looks like this. Okay. You get a corner that looks something like this. Okay. Half less than m less than 1, okay, and the flow looks something like that. Okay. Once again, these two lines 0 and pi by m, 0 and pi by m are lines along which there is no velocity normal to the lines, and therefore, these constitute valid bounding surfaces for the flow. Okay. Okay. So, this angle now is pi by m. This angle now is pi by m. M is less than 1, but greater than a half. So, the angle is greater than pi, but less than 2 pi. Okay. And one can have a flow solution for which the angle is actually 2 pi. Okay. One can have a flow solution for which the angle is actually 2 pi. Okay. That happens for m is equal to a half. So, that the angle pi by m is pi by a half, which is 2 times pi. Okay. So, therefore, I have a surface that looks like this. The angle around is 2 pi, and the flow field will look something like this. Okay. The flow field comes in on the lower half plane and goes out on the upper half plane. So, these are the kinds of velocity fields that you get if you consider simple functions which are some powers of the complex number. The lowest power that you can have is z power half, m is equal to a half. In that case, the angle is equal to 2 pi. Okay. Between half and 1, you have an expanding flow. At m is equal to 1, it is just a constant velocity. M is equal to 2 is in a right angled corner, and greater than 2 is an acute angled corner, and less than 2 is a corner with angle greater than pi by 2. So, these are simple forms of the these are power forms of the complex function. Now, after considering simple powers, the next thing to consider is a logarithmic function. Okay. So, f is equal to m by 2 pi log z. Okay. So, therefore, the complex velocity w is equal to m by 2 pi z is equal to m by 2 pi r into e power minus I theta. Okay. So, that is the complex velocity. We know that this has to be equal to u r minus I u theta e power minus I theta. So, therefore, we find that u r is equal to m by 2 pi r, u theta is equal to 0. So, this represents a radial velocity profile. Okay. The velocity field everywhere is always radially outward. Okay. So, at some location the velocity field is always radially outward. Okay. Note that the magnitude of the radial velocity decreases as r increases. The magnitude of the velocity goes to infinity at r is equal to 0. Okay. So, at the origin itself the velocity is infinite. As you go outward from the origin, the magnitude of the velocity decreases as you go further and further outward. However, if you calculate the flux, total mass flux coming out, the mass flux coming out of a surface such as this one, the mass flux coming out of a surface such as this one can be calculated as flux is equal to integral over the surface of u dot n. Okay. The unit normal to this surface, since I have taken a circular surface, the unit normal is along the radial direction. Therefore, u dot n is just equal to u r itself. Okay. Integral ds u r. Note that as I discussed at the beginning of this lecture, this flux in 2 dimensions has to be per unit length in the third direction. Okay. So, this is a flux in 2 dimensions, that is, rather than mass per unit area as it is in 3 dimensions, this will be a mass per unit length, okay, per unit length perpendicular to the third direction. Okay. So, in this particular case ds, the surface is just a line. It is the line along that circle, okay, because I am taking it per unit length in the direction perpendicular to the plane. Okay. So, that ds is just equal to integral r d theta, okay, because along this line r is a constant, it is theta that is varying all around from 0 to 2 pi. Okay. Along this line r is a constant. So, theta goes from 0 to 2 pi, okay, into m by 2 pi r. Okay. So, even though the velocity is increasing, this flux, okay, you can easily do this integral, r and r will cancel out, m d theta from 0 to 2 pi divided by 2 pi will just give you back m. Okay. Even though the velocity is increasing as you go towards the origin, the amount of mass coming out per unit length in the third direction is remaining the same. Okay. So, what that means is that if you take any surface here, okay, any surface here, the amount of mass coming out of the inner surface, okay, the velocity at the inner surface is larger, the surface area is smaller, the amount of mass coming out is the same, that is equal to m at each and every surface. That means that there is no source anywhere in the flow except right at the origin. Okay. There is no source anywhere in the flow except right at the origin. Okay. And because of that, the velocity turns out to be 2 pi r. Okay. If I calculated the complex potential for this case, I would find that it went as log of r. Okay. In 2 dimensions, a source of mass, a source of heat, the temperature or the potential goes as log of r. In 3 dimensions, it is proportional to 1 over r. In 2 dimensions, it is proportional to log of r. That is obtained by solving the Laplace equation in 2 dimensions. Either for the temperature or for the potential. You can easily see that the solution of this is log of r. So, when I took this form log z for the potential, that corresponded to a point source right at the origin in 2 dimensions. The velocity decreases as 1 over r as r goes to infinity. The surface area increases proportional to r, therefore, the mass coming out of any surface is the same. there is a delta function source at the origin, and that is generating a radially outward flow in this two-dimensional plane. There is another important logarithmic dependence that can give you an important flow. Okay. Let us look at that. F is equal to minus I gamma, okay, which implies that W, which is equal to df by dz, which is equal to minus I gamma by 2 pi z. Okay. Expressed in terms of r and theta, this turns out to be equal to minus I gamma by 2 pi r e power minus I theta. Okay. And I can write this as usual as u r minus I u theta e power minus I theta. So, clearly u r is equal to 0 because the coefficient of e power minus I theta is purely imaginary. Okay. So, therefore, for this flow I have u r is equal to 0 and u theta is equal to gamma by 2 pi r. Okay. So, therefore, along any particular circle over here, u r is equal to 0, there is no radial component of the velocity, u theta is equal to gamma by 2 pi r. Okay. So, therefore, the velocity u theta, okay, note that u theta is defined to be positive in the anticlockwise direction, in the direction of increasing theta. Okay. Therefore, u theta is a constant everywhere along this, and this represents a flow that is circulating around this origin. Okay. This represents a flow that is circulating around this origin. Okay. So, the flow is circulating around the center of this coordinate system. Okay. What is gamma? Okay. In a similar manner to we found out the mass flux for a point source at the origin, gamma is what is defined as the circulation, and that is obtained as follows. Okay. The circulation is defined as integral over the surface of integral over a closed contour of dx dot u. Okay, integral over the closed contour of dx dot u. Okay, where dx is the tangent vector along the contour. Okay, so, if I have a contour, at each point I have a tangent vector along that contour. Okay. So, you can see that for this circle, if I take dx dot u, for the r component of the velocity, dx dot u will be 0. It is non-zero only for the theta component, the component that is tangential to this surface. Okay. So, this circulation around the circle is equal to integral dx dot u. Okay. And this, in this case, okay, this dx is given by r d theta times u theta. Okay. Dx is r d theta along the surface times u theta, okay, because the theta vector is along the direction of the displacement along that contour. Okay. So, this will be equal to integral of r d theta times gamma by 2 pi r, okay, which is nothing but gamma itself. Okay. So, therefore, the u theta velocity, the theta velocity goes to infinity as you go towards the origin. U theta goes as is equal to gamma by 2 pi r, but the circulation along any contour is exactly the same. The circulation along any contour is exactly the same. Okay. So, this is what is called a line vortex, okay, a line vortex in which the circulation is exactly the same on each and every contour. Okay. Note that I have got a velocity field which seems to be rotating. Okay. When I started off, I said potential flow irrotational, there should be no rotation. Okay. I have defined here for you a circulation, okay, which is basically integral over the surface of dx dot u. Okay. So, apparently it appears that the velocity field is rotating, but that is actually not so. Okay. The reason is because local rotation depends upon the local antisymmetric part of the rate of deformation tensor. Okay. Now, a velocity field will be rotational only if locally at points within the flow there is a non-zero antisymmetric part of the rate of deformation tensor, or there is a vorticity somewhere within the flow. Okay. This what we have is what is called a line vortex. Okay. And note that we had done the Stokes theorem earlier when we discussed vector theorems. Okay. And that Stokes theorem, what it told us was that integral ds of n dot del cross A is equal to integral over the contour of dx dot A. Okay. So, the idea was as follows. Okay. I have some surface with some bounding contour on it, okay, and the vector A is defined everywhere on this surface. And what the Stokes theorem said was that integral over the surface of n dot del cross A, okay, that is everywhere over the surface, if I take n dot del cross A and integrate it over the entire surface, it is actually equal to the integral over the perimeter of this surface, okay, taken in the anticlockwise direction as appropriate for the curl, the perimeter of the surface, okay, of dx dotted with A. Okay. So, that is what the Stokes theorem said. Consider that we are considering now a two-dimensional system. So, that the surface is now in the xy plane. Okay. So, that is our two-dimensional flow. Okay. The surface itself is a surface that is in the xy plane. Okay. The surface itself is a surface in the xy plane. The unit normal to the surface is in the z direction. Okay. The unit normal to the surface is in the z direction, and my contour goes in the anticlockwise direction in the xy plane. My contour goes in the anticlockwise direction in the xy plane. Okay. Then for this particular case, I will have integral, okay, over the surface, that is the surface ds, n dot. I consider this vector A to be the velocity. So, del cross A is just the vorticity. It is equal to integral dx dot u. Now, what this implies is that integral dx dot u, which was the circulation, okay, I just calculated this as the circulation. So, this integral dx dot u is non-zero for this particular case. Okay. Note that it is a two-dimensional flow. I had assumed that the potential flow was irrotational, therefore, n dot omega has to be equal to 0. Can I have a situation where the left hand side n dot omega is equal to 0, whereas the right hand side is non-zero? Right? Clearly, it seems it is not true. Okay. The answer to the paradox is as follows. The vorticity itself is a delta function along the origin here, okay, along the z axis. Okay. So, for this two-dimensional flow, one can consider the vorticity in 2 dimensions to be a delta function right at the origin. Okay. That means that there is a vorticity at the origin itself, but there is no vorticity anywhere else in the flow. Okay. So, therefore, what will happen is that if I take a two-dimensional plane, okay, and I go all the way around the origin, okay, since the vorticity is a delta function at the origin, the circulation here around this surface will in general be non-zero, okay, because only at the origin I have a delta function vorticity. Because of that, the circulation is non-zero in any contour that includes the origin. However, if I take some contour somewhere within the flow that does not include the origin, there the circulation will be 0. That is because the vorticity is 0 everywhere. The fact that the vorticity is 0 everywhere is reflected in the fact that the circulation along any contour is exactly the same. Okay. So, if my surface cuts the z axis, cuts the origin, the vorticity is a delta function there, and therefore, I get a non-zero result. If it does not cut the origin, then the vorticity is 0, because the vorticity is a delta function. Omega is equal to gamma delta function in this two-dimensional plane. Note that the delta function in a two-dimensional plane has dimensions of 1 over length square. Okay. The circulation is velocity times length gamma, as the vorticity goes as velocity divided by length. Okay. So, for this flow with omega is equal to gamma times delta of x, the solution is u theta is equal to gamma by 2 pi r. Okay. Just as in the case of the mass source which we just considered, there is a source at the origin, but everywhere else the flow is incompressible. Similarly, in this particular case, there is a delta function vorticity at the origin, but the flow is irrotational everywhere else. Okay. So, this is the flow around a line vortex, for which the function f of z is equal to minus I gamma by 2 pi log z. Okay. So, this is a line vortex. M by 2 pi log z is a point source, or a line source at the origin, a point source in 2 dimensions and a line source in 3 dimensions. This is a line vortex. In the next lecture, we will look at some more complicated forms, in particular the flow around a cylinder, and our objective will be to calculate the net force that is exerted for the flow around a cylinder in 2 dimensions in a manner similar to the force that we calculated for a spherical object in the last class. In that case, we found that the net force on a sphere has to be 0, because there is no viscous dissipation. In this case, we will see that it does not have to be 0. The net drag force along the direction of velocity has to be 0, but the net force perpendicular, what is called the lift force, does not necessarily have to be 0. So, in the next lecture, we will look at the velocity field around a cylinder in 2 dimensions, rather a circle in 2 dimensions, or a cylinder, infinite cylinder in 3 dimensions, and we will calculate the net force on that after calculating the velocity field. Okay. So, we will continue this in the next lecture. We will see you then.